Hey there! In today's video we will be playing around with Proxmox and LXC containers and storage. And if you happen to run Docker containers within those LXC containers, then this video will be especially useful for you. Interested? Keep on watching. But first, if you're new to the channel, my name is László Merca, and this channel deals with home automation, home networking, and sometimes with related stuff like DIY electronics and even a little bit of 3D printing. Anyway, let's continue with today's topic. If you're a returning visitor of the channel, you might remember that some time ago I published a video about how to use Proxmox and LXC containers to run Docker containers inside. Now, by the end of that video, I quickly explained an option to mount up storage so you can use them from those containers. But because of the time constraints of the video, I instead of a normal explanation just suggested a quick solution, which is understandably not the best. It's more like a hack and not a real life situation. So for this current video, instead I came up with an example situation. It's like this. So this is what we will discuss. For many people, it's quite normal. You have a NAS that stores your data, and you are running multiple containers that might want to share the data between them. So I will just go through this and explain what steps you need to take to make it all secure and have those folders accessed properly from within your LXC or from your Docker containers. Now, to value your time by keeping the video short, and for the sake of demonstration, I already created two LXC containers within my Proxmox host. So these are the two, and within Proxmox, I will just quickly show you the configuration for them. So for that, I opened up my shell on the Proxmox node, and there we go. This is where you have the configuration file for your LXC containers. So these are the two that we need to inspect. I will just do a quick diff because I have something to show you. So as I explained in the previous video, you need to mount your local folders via something called a bind mount. This is a feature of Proxmox, and I've already done this for the first container but not for the second. So to do that, you will just need to edit the file at the line like this. This is more like a quick reminder from the previous video. This is already explained there, but in general, this is the folder on your host. This is the folder where it will appear, the mounted folder within the container. So I just quickly edit the configuration of the second container. There we go. I add the mount point, save it, and restart that container. In case you have successfully managed to do it, it should also appear here as a mount point. Also, you can use the UI to edit. I just prefer editing the configuration files where I can. Okay, now back to Proxmox. So I have this folder here. This is pretty empty, just holds an empty file. I will tell about that later. And this resides on the ZFS storage of my Proxmox node. And now this should be accessible from both containers. So I just open the second one and then open the console, log in quickly, and let's just check out that folder. It's there as expected, and the file is there as well. Now here comes the interesting part. What if I want to write into this file and I want it to appear in the second container? So we just have to check the access rights quickly. This looks pretty good. It's accessible via the root user, which is the user I logged in with. So I should have no problem of it running into the file. So I can just open it in editor, write whatever I want, save it, and if I go to the second container, log in here as well, go to the same folder because it mounted to the same point, I can instantly see my changes. But here's a trick that I needed to do to make this possible. So by default, when you create a folder on the host, it is assigned to the user and the group that created it. Now, that user could be a root user or anything, and that means it won't be accessible from the containers by default. This is why we needed to apply that hack in the previous video. Okay, and what should I do to make it properly accessible? Especially if I'm not using the root user within the container, because, well, it's not that secure. I mean, if you use this container and log in, you might not want to use the root user all the time, which is understandable. So here comes the interesting part. We need to learn about how users from within the container are mapped to users outside the container. This is important because those users might or might not be the same. I mean, I can have a user called John here inside the container because it's like a slim operating system. It's running systemd, running services, running Docker, and obviously I can create users and pass around access rights to various folders. But having a folder on the host might be totally different when it comes to access rights. So what happens if I don't have that user outside on the host? So it's assigned to another user called Eve or whatever. What will happen then? We need to map these users somehow, and this is what I will show you now. To better understand the whole user mapping idea, we need to get back to the roots. Yeah, pun intended. So we just go back to Proxmox shell, and then we check out the folder we have on the host. That is, in my case, this one. Now, you can see the access rights here, and it looks weird. So if I go back to just one folder and do the same here, wow, what's happening here? What is this number? So you might remember that all the users in Linux and all the groups have their IDs. So for users, it's called a UID. For groups, it's called group ID or GID. So if you just do this, you can see the IDs and the groups of the currently logged in user. So what is this big number? Because apparently there's a difference here compared to the other folders. This is a mapped ID. What on earth is a mapped ID, you might ask? Well, it's a user ID which belongs to a user that is not present in the host operating system but exists in one or more containers. This is needed because each LXC container runs its own OS, and because of that, user IDs between containers and the host OS can and probably will overlap or clash. Think about root, which has the ID of 0 each and every time you install a new instance of Linux. What if you want to have a folder on the host that is only accessible to one of the containers? Each container has a root user, and you need to differentiate all those root users from each other somehow to configure write access separately. So how does this mapping work? It's simple. Let's take a look on this example. We have two containers. One is owned by a user called John, and then there's another owned by Eve. Inside their containers, they both want to run their stuff, and they both want their containers to access their folders on the host. However, as I mentioned before, their IDs will overlap. Both will be 1000. If you create local users for them on the host, the IDs won't match. At least not for poor Eve. So what can you do? You can use the ID mapping feature of the containers to create users for John and Eve with IDs that will be mapped to their user IDs from within their containers. With the mappings, you can avoid clashes, and with the users you will also create groups which can be used to connect actual host users to these internal users. The mappings are defined in the LXC configuration files of each containers. Let's see an example. To see or change the mappings, you have to do the following. So you open up your Proxmox's web interface, then go to your host, select shell, and this is where we need to edit the configuration file. If you've done this before, then it's pretty much the usual stuff. So you check the ID of your container. For demo 1, it's 105 for me. So I will just check out the file /etc/pb/lxc, then the id.conf. As you can see, I already created this mapping. This is for the container that is used by the demo user John. These two lines are the mapping that you want to have. So the first one defines mapping for the user, the second one defines mapping for the user's primary group. What do these numbers mean? 0 means the first ID that you want to map, 1005 means the last ID you want to map, and this one is the offset. So that means root will be mapped to user ID 100,000, while John with the user ID 1000 will be mapped to 100 and 1000. If the mapping is not defined yet, or you want to change it, then you can edit this file here, and after that you have to restart your container. Before continuing, let's take a look on the user mapping and the container of Eve, because there things will be a little bit trickier. So just let me show you the configuration file, and as you can see, it's quite a bit more complicated. So first of all, if you don't specify anything with LXC containers, your default mappings will look like this. So it means that all users starting from 0, the root user, and up until 64K will be all mapped to this range. You might remember that in case of Eve, we wanted to have something pretty similar to John's, like having a small set of user IDs mapped to a different range. So how on earth we ended up with this one? Actually, this is the way I do it. I'm not saying this is the best way, but since the information on this topic is quite scarce on the internet, I come up with this solution after quite some time spent on investigating. So what you need to know is that if you go outside of the default range, then you will face problems if you only add these two lines. Actually, you can try. If you do this, then your container won't be able to boot properly, because apparently the root user will lose its access rights to quite a few important system folders. So first of all, I ended up with the idea of having users with ID and GID under 1000 kept in the separate mapping. So this is like keeping all those users that includes the root in the default range. And this worked out fine. However, I want to have all the additional users that I create after that, that includes the user of Eve with the ID of 1000, to be mapped to this new range. Finally, about the last two lines, I decided to have those because apparently there are some special users that are used by Linux and they reside on the upper end of the default range. So for example, with the user ID 65,534, you have the user which is called nobody, and it has a matching group called no group. And this one is also special. So think of it more like a template. I mean these 6 mapping lines that I use on a daily basis for containers. And in my case, it ensures that I won't mess up those service users with the small IDs and the special user like nobody with the high ID, and I still have 64,000 user IDs and group IDs that I can freely map within these ranges. Also, if I want to separate containers clearly, then I can just keep adding ranges like this. Okay, what next? So are we finished yet? Unfortunately not. You will have to enable these ranges besides the default range. By default, this range is okay for you, but if you start using a higher range like this, just like that, once again, you will face problems. So what you need to do is you need to check out and actually edit two system files. So those are located under the /etc folder. So let's see /etc/subuid. This is the one of the files, and the other one is subgid. So let's start with the first one. As you can see, I already added this entry. By default, it only had this line, which is the default range. You define a starting offset and you define a number, which is the number of IDs you want to use, and also you define a username which will be able to use these mappings. So this means that the root user can use 64k IDs starting with 100,000. And then the next line, the root user can also use 64k IDs starting with 200,000, and these can be used for mapping. Why do we need to mention the root user here, you might ask? Well, that's because the root user is the one that is running our LXC containers. So actually all these mappings will run with the root user that is running the process. The other file is for group IDs, and it's very similar. Those files can be identical, and it's normal. So now that we have added this extra range to both files, you need to restart the LXC service, which reads these files. So that is like system control restart LXC. This will actually restart your containers as well. So yeah, this can take some time. Just a quick recap on what we have done so far. So we started with setting up mappings in the /etc/pv/lxc /whatever containerid.conf files for each containers. And then we enabled the extra ranges we have come up with during the mapping definitions, and added those on the /etc subuid and /etc subgid files. So question is, are we done yet? And nope, we are still not done. So what next? At this point, our container with the new mappings should be able to boot just fine. If you have previously created the users like John and Eve, you can even use them to log in. So in my case, I created the users because I don't want to waste more time on this. And yeah, John is created for container 1, Eve is created for container 2. So in case of container 2, I just use the user of Eve to log in. Here we go. And if I go to the folder that is mine mounted to this container and check out its contents, I can see there's a problem. So I won't be able to write here with the user Eve. And that is because by default, when a container is running with a bind mount, those bind mounts will be assigned to a root user. Unless, of course, on the host, I change the ownership of this folder, I mean the mounted folder, to the mapped user ID. Okay, how do I do that? So I just go to the host, go to that folder. You can see these folders that are bind mounted to the containers are now owned by the root users of the containers, which is not too good for us at the moment. Okay, so you can use the command chown to assign the ownership of the first one to John, and do the same one, the second one for Eve, like so. Now if I go back to the container of Eve and do this again, no problem, I can write a file here because these have changed. To be honest, I have to stop here for a second and explain a small correction that I had to make in the second container's configuration file. The example I shown before was slightly wrong, so let's see what have changed. Actually, I needed to change this offset from 200,000 to 201,000, and this totally makes sense because Eve's user as the first user in the range belongs to this offset. So this is the only change that I needed to make, and yeah, after that container restart yada yada, and now we are back on track. By the way, if this is starting to get way too complicated for you, don't worry. There's a different, somewhat easier way to work with mappings, but let's get back to that later after finishing this example. Also, as usual, you can use the comment section of the video if you have any questions, and I will be happy to answer them. So, what we have done so far is super cool. Our containers can write folders without relying on the root users, and we have a fine-grained control over who or what can access what. Again, if you provide separate mappings like I did, you can separate their mounted folders based on ownership, or you can use the same mapping inside those containers and have them share their working folders. But wait, there's more. So these numbers on the host look a bit weird. I mean, not really user-friendly. So what if we could turn them into actual group names and usernames right in the host with only a few commands? Yeah, let's do that. So we will just create some fake groups and users for these mapped users, just for the sake of readability. This is totally optional. If you're fine with having these numbers, these IDs here, then you can skip this part. But if you are curious, let me show you how I do that. So first of all, I will just add the group with the exact same group IDs. I mean, add two groups. Then let's do the same for Eve. Now I check it out, you can see it's already starting to look better, but now let's create those users as well. So it's a little bit of a longer command because we take some precautions, like these users cannot be used for logging in, and no home folder is created, no shell is assigned whatsoever. So the command looks like this. This is where I specify the primary group for the user. This is where I specify the user's ID and yeah, the user's name. Boom. Once again, the same for the other one. Here we go. Now these mapped users look much better with their groups. Also, these groups have a second purpose. So, for example, if you have a user on the host that you want to use to write and read the files of the container, like John has his own user and Eve has her own user, you can use these groups to do that. So, we will just add John's user to this freshly created John-LXC group. To do that, I use the usermod command. Yeah, obviously I forgot to create the user for John. So let's just do that. I will use this usermod command, but I need the shell because I want the user to be able to log in, and yeah, I want to have a home directory for that user like a normal user. We will also need that later for some configuration, and I don't really care about the IDs. And yeah, so this is it. This warning you can ignore. I just had some experiments in the past. Don't worry about that, it's just some leftover folder. Also, I'll do the same for if. Yeah, same situation. If those are freshly created users for you, you won't see these messages. Now, back to the user mod command. Now I can add it to that group. And let's do the same for if. Okay. Now, what happened? If John logs in with his user, obviously you have to assign a password and stuff like that, but that's outside the scope of this video. So let's assume that your user John logs in and wants to write files on the storage that are also writable by the container. So can we do that already? Well, to be honest, some small details are still missing. But first, once again, a quick recap. So what we have done so far, we have set up our mappings, then we enable those extra ranges, then change the ownership of the bind-mounted folders on the host to the mapped UIDs and group IDs, which made them writable by non-root users inside the container. Fine. Then, for the sake of visibility, we have added fake groups and users on the host, so IDs like 101,000 appear as usernames and group names instead of these cryptic numbers. Then finally, we have added our local users to these new groups, so they can write into bind-mounted folders as well. Question is, are we done yet? As I mentioned, sadly no, but we are nearly there. Now, regarding those small details. First of all, if you, let's assume, log in as John and try to create files on the folder that is bind-mounted into the container, you can run into some issues. Let me show you one. Okay, permission denied. Means I cannot write into this directory. Although the container can write here, I still cannot write. This is not good. So what could be the problem here? The problem could be is that when this folder was created, then its access rights were defined in a way that the creator user, which was root back at the time, can write into them, but nobody else. As you can see the rights here, there's a W missing. Okay, so to fix this, you just get back to root and use the chmod command like so. Okay, let's go back to John and try again. Nice! Now John can write files into this folder. However, there's still a problem. If you check the file, you can see it's created with John's user, which is fine. On the other hand, the group has only read access for that file, which is not fine. And this is where the umask setting comes into play. Umask is a setting that you can use to set with what kind of default permissions files are created. It's technically a coded number and looks more confusing to calculate than it actually is. Many people use an online calculator for this purpose, like this one. As usual, you will find the link in the video description for this calculator. In our current case, we can rather simply look at umask as a number that is used as a complementer of the number used to specify permissions with the chmod command, for example 755. Umask as a setting can be manipulated with the command which is also named umask. You can use it to query the current setting, and you can use it to set a new one. About calculating its value, here's an example. If I want my files to be created with permission 755, umask has to be 0022. Why? Because the simplest way to calculate umask is to subtract all digits of the desired permission number from 7 one by one, and then finally prepend a 0 to what you get. So to have our files created with 775, which means the group has write permission as well, umask has to be 0002. Like so. So you can see that now the demos3.txt file finally got created with the proper permissions. And that means both of the users can write the file from inside the container and from outside the container on the host with this user. So we could say mission accomplished. At this point we are done, we have reached our goal, but still there's a last thing we need to do. So as you can see, I just logged out with the user John, and now I log back in and see what happens. Okay, that is not good. That means our umask setting can't hold its value between logins. To do that, you need to issue the umask command in a file based on your operating system, based on your shell of choice that runs on every login. So since I'm using the bash shell, a file like the bash rc or even the .pro file should suffice. So for example, in my case, I can just edit John's profile and add umask 002 here, exit, and there we go. Now if I log out and log in again, my setting is preserved. Okay, now we are fully done, I promise. You might also remember in the video I mentioned that there's a simpler solution to work with these user ID mappings, and that in the end I will show it. So let me show you a quick example. I promise it won't take as long as this whole crash course so far. First of all, you need a user that you can map to your container, because the idea here is that we are doing the reverse. We are not mapping users from inside the container to the OS, but we map users from the OS into the container. That means we need to create the same user in both operating systems, both on the host and inside the container as well. So let me quickly do that. As you can see, I created the user dummy both on the host and on the inside the container. And as you can see, there's a side problem, which is actually good for us because it will demonstrate our mapping a bit more. So they have a different ID. 1001 inside the container, 1002 on the host operating system. So we will have to deal with this. But don't worry, it won't take long. Now we define a mapping on the host operating system, so we can map the user from the host into the container. For that, I will have to edit this file. Once again, I have already prepared the contents, but let me quickly explain the changes. So I took the original file from the previous example and left the mapping for the service user with IDs below 1000 intact. In fact, I changed the upper limit to 1001 because I also want the first user of the container, which is named John, left as it is. We just simply don't care about that user anymore. On the other hand, since I need to map the user dummy, which has the ID of 1002 on the host, but 1001 inside the container, I needed to add these third and fourth lines, which mean map a single user with the ID of 1001 to the host user with the ID of 1002. And yeah, the count is 1 because it's a single user. Finally, I needed to edit these fifth and sixth lines because, well, I need to tell LXC what to do with the other users. And this means basically that any other users which has the ID of 1002 or any larger inside the container, we don't care about those. Let's just map them the usual way. So as you can see, this is the rest of the range, and this is the basic, the first user ID mapped to the first user ID of the range. Okay, cool. So we're done with this file. We need to save it, exit, and yeah, we are almost done. Don't forget, we also need to add this extra range to our subgid and subuid files, because this is also outside the usual range. So let's edit those files as well. We can actually get rid of these. These are just auto-generated. What matters for us is root. Because we have touched the subuid and the subgid files, the usual rule applies, means that we need to restart the LXC service. So once again, now you can use your dummy user in the container to write into the mounted folder. By using this user, you can still face two kinds of permission issues though, and here's how to quickly fix those. So first of all, you probably can't write into the mounted folder from within the container. The solution is that you need to make sure that the mapped host user is the owner of the folder outside the container, or at least has the right permission for it. In my case, it's still assigned to the user John from the previous example, so we need to simply grab the ownership. For that, you need to go to the host and change the ownership. Now, if I go back to the container, I should be able to write into this folder. Here we go, this is solved. The second possible permission issue is that when you take a look on the home folder of your user inside the container, you will see that now everything is owned by well, a special user called nobody and the group called nogroup. This is because we have basically remapped our user, and when the home folder was created for it, well, it belonged to a user that wasn't mapped. Unfortunately, the obvious solution doesn't seem to work. I mean, yeah, I tried grabbing the permissions and the ownership of the folder with the root user, like this. So, what I could find out though is that to avoid this mapping clash, the user must be created after it got mapped. Next, I tried deleting the dummy user with its home folder and recreating the whole altogether with the same ID, so hopefully the permissions would be in order. However, since the user existed before the remapping, now I can't do this. What I can do though is that I shut down the container, remove the mapping, reboot the container, remove the user, then redo the mapping, reboot the container once again, and then recreate the user after it has been mapped. And that should work. Now let's reboot the container without the mapping. Once again, we shut down the container. Now we re-add the mapping. And once again, restart the container. recreate the dummy user with the exact same ID. Now let's try logging in with the dummy user. And voila, home folder permissions are in order. Now let's see the mounted folder. Seems alright. There we go. Looks good so far. Now let's try to modify the same file from the host. And yes, we are done. But hey, what about Docker? I've promised Docker, right? Okay, let's do that quickly. So here we go, but let's assume that you are able to run Docker containers within your LXC container with your dummy user or whatever user you are using. If it's not working, as a reminder, here are two things to quickly check. First, in the LXC configuration file, in the container configuration file, you should have a line that enables container nesting. This line should be there. If it's not there, then add it, then restart your container. Now, the second one that you might need to check is within the container itself. So the user must be part of a group called Docker to be able to run Docker containers. You can check that by using the id command. It should be there. If it's not there, then you can use your root user to modify the user like so. This command should handle it for you. To test it, actually, you can use Docker's built-in hello world container like so. If this doesn't give you any errors, then you're just fine to run any containers. Okay, let's see whether we can write a file that is on a host mounted through the LXC container, like so. Normally, this command does not give you any output, but in fact, it does the following. So it mounts up the folder, which is bind mounted into the LXC container, into the Docker container inside. It will be also at the same path /demo. Then it will use the user ID you provide and the group ID you provide, which is the ID of the dummy user. So files written will not be owned by root, but will be owned by this user and this group. And it will run this command inside a container which is running in an Ubuntu operating system. So let's see our host to see whether the bind mounted folder indeed contains this file with the right permissions. And here we go. As you can see, our file there with the right permissions freshly created, and I can even edit it and read it from the container. Now we are fully done, and we have reached the end of this whole crash course. If you have any questions left, please use the comment section of the video as usual. And that's it. This is what I wanted to show you today. So, if you found the video useful and would like to see more and haven't subscribed to the channel, then please consider subscribing. That helps me a lot. Also, once again, thanks for watching the video and really hope to see you next week with a new one. Bye.